Now that we know the fundamental theorem of calculus, we've seen that derivatives and integrals are really opposite things. Both of these take a function, give us something new. Derivatives give us a new function to work with, and integrals, a definite integral, gives us an amount of area. And we used this to build up a new function. I've been calling these area functions for a different value of x. Integrating between a and x gives me a different amount of area. So sure, that's the description of a function, even if the formula is a bit convoluted. And the fundamental theorem of calculus tells us that these operations undo each other. So with that in mind, everything that we know about derivatives is an opportunity to learn something about integrals. I know that the derivative of x cubed is 3 times x squared. Well, that means that one of the antiderivatives of 3 times x squared is x cubed. And I can use that antiderivative to compute definite integrals, the same way that we've been doing for a little while now. So the more of these things that we know, the more antiderivatives we know, the more kinds of integrals that we can calculate. Now, calling something an antiderivative feels kind of manufactured, right? I just did the opposite because I wanted to. Didn't really feel like there was a motivation for it when we were learning about these things. Another name for an antiderivative is an indefinite integral. So the word indefinite here is helping to distinguish between the definite integrals we've already been working with. A definite integral has a start and a stop, and for that reason describes a certain amount of area. An indefinite integral does not have a start. An indefinite integral does not have a stop. And so the symbol that we use is exactly the same integral sign, just without the upper and lower bounds. Again, no start, no stop. There's not an amount of area I can compute for this. This symbol is just telling me, can I find the antiderivative of my function f of x? Now, as I was saying, the more antiderivatives we know, or the more indefinite integrals we know, the more areas we can compute. Every one of these formulas is a derivative formula, but turned on its head. So each of these integral signs is denoting an indefinite integral. When I try to find an indefinite integral, my answer is a function. It's an antiderivative. And it comes with this constant plus c. We've known about these for a while now because antiderivatives are not unique. One single function has many, many different antiderivatives. They look mostly the same, except they will have a different constant added on to the end. So without extra information, it's traditional just to leave a plus c at the end. So the name for this thing is called the constant of integration. Anytime we have an indefinite integral, there will be some antiderivative with some constant of integration. We can at least know what that antiderivative will look like, but we won't know what the constant is unless we know a little bit more about the problem that we're given. So here we have indefinite integrals for some common functions, for constants, for powers of x, for the reciprocal of x, for exponential functions and trig functions, and even some of the inverse trig functions. It's very common to refer to tables like this. You'll find these in the backs of most calculus textbooks, including the one that we've been using. And they're not too hard to find online either. Now, I'm not wanting to stop the lecture just here yet. I want to talk about how do we find more complicated indefinite integrals. So of course, I'm interested in finding and computing areas, but if I can do an indefinite integral, then all I'm missing are just the two endpoints, and I can do my antiderivative evaluated at the upper endpoint minus the antiderivative evaluated at the lower endpoint. That kind of computation we've been doing for a while. So, like other operations in math, there's an expectation that if we have two different ways to write the same function to start with, and then we do the same thing to both versions, we should get the same answer, right? That makes sense. If the only thing that's different is just the way that I've chosen to write things, what's an example of that? Well, I could have the function x squared plus 2x plus 1. That's a fine function. It's a quadratic polynomial. And if I've chosen to, I could have written it as take the quantity x plus 1 and square that, right? These are just two different formulas for the same function. Either of these calculations produces the same number at the end of the day. Well, if these things really are the same, if they describe the same function, then their integrals should be the same too. So over here, I've got the integral of my function dx, and I've got the integral of my factored version of the function, also dx. These should be the same as each other, right? Well, over here on the left, I can use my power rule. I'm supposed to get x cubed divided by 3, and I'm supposed to get x squared, and I'm supposed to get plus x. That would be using my power rule, and then I'll have some constant of integration. But what do I get on the right side here? It looks simpler, but it's not clear to me how I would perform this indefinite integral. or how I would calculate this antiderivative. Remember, those words actually mean the same thing. So what I'm going to do is I'm going to use a variable substitution. So I'm going to say that everywhere I see the quantity x plus 1, I'm going to give that a new name, and I'll call that u. This is something that we do in algebra sometimes. We change the variable a little bit. We give it a new name, and that makes calculating a bit easier. So let's take a look. If I did that, I would have the integral of u squared. I'd have the integral of u squared dx. That doesn't quite look right. The differential in my integral symbol is telling me what variable matters. And as written, that's supposed to be x. So I need to take my substitution rule right here. And what I need to do is I need to figure out how this rule changes the differential for my variables. So this is something a little bit more advanced than just changing variables in algebra. In calculus, every time we change variables, like the formula I'm using here, u is just a different name for x plus 1, then what I need to do is I need to calculate the differential of both sides. And this is the same way as we've been doing for implicit differentiation. You might remember that from a couple weeks ago now. So what's the differential of my x plus 1? Well, I'll have a dx, and the differential of a constant is 0, so I'll just have a dx. This all is supposed to be equal to the differential du. So every time my x changes, my u changes by exactly the same amount. I picked this example to be a little bit easy, since the only thing different between x and u is that x is 1 less than u, or you could say that u is 1 more than x. These kinds of changes are directly equal to each other, right? I don't care that u is a little bit more of x. If one of them gets bigger, they both get bigger by the same amount. So I'm going to make a substitution for my differential here. I've got the integral u squared du, and I'm supposed to have this equal to, well, my antiderivative is going to be u cubed all on 3. So is u cubed divided by 3 equal to what I have on the other side of the equation? X cubed on 3 plus x squared plus x plus a constant. Well, after I compute the integral, the indefinite integral, I need to change my u back into an x. How else can I compare these things if they're written as different letters? So let's take a look at that. On the left side, Nothing has changed so far. In fact, I'm just going to leave the left side as I've already computed it. Again, this is x cubed, all on 3, plus x squared, plus x, plus a constant. And I don't know what that constant is. On the right side, I've got u cubed divided by 3. And there will be another constant of integration over here. And I'm choosing to write this as the letter d. You know, maybe this is a slightly different constant. So I need to take the cube of x plus 1. Whatever that cube is, I need to divide by 3. So when I perform this cubing, I'm going to get x cubed. When I FOIL it out, there's 3 different ways I can get x squared. So I've got plus 3x squared. There's 3 different ways I can get x. So there's 3 times x. And then there's 1 way I can multiply out and get a 1. All plus my constant. And yes, everything here has to be divided by 3. So I get that left-hand side. X cubed divided by 3 plus x squared plus x plus a constant. So I really did need to have a different letter here because my constant c is different from my constant d. Somehow this extra 1/3 got sucked into my antiderivative. Now, in general, the way that this rule works, this is called the substitution rule. And the idea is that we are going to undo the chain rule for derivatives. So I know if I have, let's say, f of g of x, and I want to calculate the derivative of this thing, I'll have b on dx. I'll have f prime with a g of x plugged in, all times g prime of x. So if this is my derivative formula, an integral goes the other way. So to calculate this substitution, this change of variables, I need to find my new variable that I'm going to call u. So what is my u in this example? It's what we've labeled as g of x here. So my g of x shows up here. The differential of g of x is g prime of x times dx. And after I perform the substitution, I'm left with a much simpler integral. I'm left with the integral of some function of u. At the very end of my calculation, I'll want to change back into x coordinates so I can make sense out of this problem. But this technique allows me to clean up integrals that are otherwise a bit more complicated than I'd like to think about.